always forgot something. Okay. So yes. So the properties of this kind of network are more difficult to analyze than the one we have seen before, because we have something which has both local structure and some global random structure. So we won't analyze it analytically in details, but people have done it. And if you study the clustering coefficient, so remember we look at these two properties, clustering coefficient and average path length. And if we look at the global clustering coefficient, we can see that it has this shape. And what is important here is that it is independent of n. So it's independent of the size of the graph. And the problem we have with random network is that we have seen that the clustering coefficient was vanishing with the network size. So the more your network is large, the lower is your clustering coefficient. For a given, for a random network with a given p, with a given number of edges, if you make you fix the number of edges, you increase the number of the size of the network, you will get something with a clustering coefficient close to 0. While here, so it can be high. The clustering coefficient can be high. About the average distance, average path length, you see that we also don't study it, so it's also very difficult to study analytically. So we can study it with numerical simulation. So we generate network, we randomize some of the edges, and we observe what is the clustering coefficient and average path length. And what is interesting is that we see that there is something called a small wall regime here in the middle. So how to read this plot? You have here P. So P is the fraction of edges that you rewire. So here you rewire 1% of the edges, 10%, and 1 every 1,000. And you observe here what is the clustering coefficient for this value of P compared with the clustering coefficient if your P equals your original circle regular graph. And same thing for the average path length. So what we observe is that if you increase P, your average distance will decrease very quickly. So after you rewire a few edges, you already have this average distance decreasing very quickly. But you see that in the beginning, your clustering coefficient stays high. What's happening is then that somewhere in the middle here, or here, where you want, depending on where you put your boundaries, you will have an area with small average distance and a high clustering coefficient. And this is what we call the small wall regime, where you have this both these properties. So one question you can ask is this realistic? Is it what's happening in real life? Well, not necessarily. Maybe in some networks. The idea to understand intuitively what's happening is very simple. It's just that you're adding shortcuts in your graph. So you can move locally from node to node, but now you have some shortcuts allowing you to jump to a completely different part of the graph. Then you can move locally, but take another shortcut and move somewhere else very different, and so on and so forth. So if you think of a social network, it can be related to a theory called the theory of weak ties, which says that what is important for a social network to be well functioning is that you have your close friends, but you also have some distant friends that you don't maybe meet every day, but they are from maybe a different social group. So with your close friend, your family, you have a lot of contacts, but these people are more or less like you. So they all look like you, they all know the same people. So for instance, if you want to find a job, these people, they might not be that helpful because they all have more or less the same information than you. And if you, for instance, if you want to find a job, what you need to use are your weak links. So the links with people you maybe don't know that well, but that live in a very different context. Maybe people you met when you were younger, when you were on holiday, or maybe distant relatives, something like that. They are kind of long links, but they have a completely different social network than you. So they give you access to a part of the social network which is completely different than the one you have access to. And so this might be an idea of these weak links, these shortcuts that can allow you to access another part of the graph, which is well connected, but where you don't have access because you know only this person, so you have little access to. So that might be a relation you can make with the real world. So if we just look at the degree distribution, because this is something we have analyzed for the other graphs too, without going into details, you see that you start with a fixed degree. So if you have p equals 0, your degree is the same for all the nodes. And if we go towards p equals 1, we have a random network, and we have seen that in a random network, the degree distribution is Poissonian. Okay, so it's a bell shape. And if you look in details at what is happening when you're going from one to the other, actually you can approximate it when you increase a little bit p by a Poissonian distribution, which makes sense because we have seen that with a Poissonian distribution, if your network is very large, then we have seen that the bell curve is very sharp centered on the average value. So if you're going from something where everyone has the same value to something where it is centered on the average, but everyone is quite close to this mean value, then you're not changing much from one to the other. So you can approximate it by this Poissonian distribution. So you remember probably this table. We had seen that real-world network, they had a broad degree distribution, something like a power law. They had a short average distance, and they had a large clustering coefficient. And we had seen regular lattices where you could have a large clustering coefficient, but the path length and the degree distribution were not corresponding to a real network. Then we saw the Erdős-Rényi random network that had a short average distance, but small clustering coefficient and Poissonian degree distribution. Then configuration model, it has a small clustering coefficient and short. So short, you can choose the degree distribution. You have a short path length, but a small clustering coefficient. So finally, we find the graph here with a large clustering coefficient. Well, it can be large. It has a short average path length, but it has this Poissonian degree distribution. So it's still very different from most real network, where you have these hubs, these large degree nodes. So this is a problem, and we will see we will see another famous model which tries to solve this problem. But first, we will need to present in more details what is a scale-free network, so a network with a power law degree distribution. Any question on what's Strogat's small world network? So that's from this paper that we use the term small world to describe a graph which has both a short average distance and a high clustering coefficient. In some contexts, some people use small world just only for the notion of having a short average distance. A small world, so you can reach everyone quickly. But since it was really introduced by this paper, and they focus on the clustering coefficient, then usually for a small world network, we need to have these two properties. short break. Okay, so let's talk now about scale-free network. So I use the term scale-free network to describe a network which has a degree distribution following a power law. So we introduced it already briefly, but now we will see it in detail. A power law distribution means that approximately the probability of a degree of a node taken at random to be of degree k is of this form, approximately. We will detail it also later. And what is important is to see that you have this degree distribution has mainly one important parameter, which is the exponent, so that we call alpha here in this class, which is called the exponent of the distribution. We will see what is its interpretation. And here we will work with approximation which are continuous. Of course, degrees are discrete, but the theory is similar. So the scale-freeness of network, so the in particular, it's very famously studied and analyzed by Barabasi, famous researcher in network science. And one of the first plots where we see this scale-free properties of network is this one, in which they plotted the degree distribution in the World Wide Web. And what they observed is that if you plot this degree distribution on a logarithmic scale on the x and a logarithmic scale on the y-axis, you get something that looks like a line. So they said, oh, it's interesting. It's a line. But then some other people published other studies, and they looked, for instance, at the internet, and they plotted it on a log scale, and they also observed look at this degree distribution in different kinds of networks. So, for instance, here on airline route map, and so of course they found that sometimes it's not perfect line on the whole degree distribution. So here, for instance, you have a line basically from the beginning, but at some point you stop here to follow the line, maybe because there are some physical constraints. We live on a world which is finite, so you cannot have infinite degrees. So maybe it's not following the degree distribution here, the power law. Then we can look also in scientific collaborations, and maybe you need to fit a little bit. It's a little bit more difficult to find a single power law here, so you try to find several lines on your log-log plot, and you search for in sexual interaction network and in many social networks, here, where you look at emails that are set within a company, or Facebook friendship, or Facebook social graph. So people started to really take a lot of networks, search systematically for the degree distribution, and check if it was actually a power law or not. So if it was a power law, the simple way to do it is to do this log plot and check if it looks like a line. So here it's really well approximated by a line. Here, not so well. Probably it's not a power law distribution, unless maybe you want to find a line just here, but it's not very serious to do that. Yes? You mean this?
Yes, this.
It's because here you're observing something which is very rare. So this actually corresponds to a single observation. Oh. So here there is only one node with this degree, one node with this degree, and then there are two nodes with this degree, three with this degree, because it's a log scale. So actually this corresponds to a single or two observations. So it's just an artifact of the visualization, basically. Yeah, and here you see that maybe you have something strange in the middle. So yeah. So the problem is that so you can observe sometimes this line, sometimes not, but we will see later that it's a real question to, it's a difficult question to answer if there is indeed a power law or not, but we will see that there is a way to really study this seriously. First, why is it interesting? Why is it important? I already introduced this in the first class, but I will still say it again. What is very different in the power law distribution is that it's not a bell-shaped curve. So this is a bell curve, Poisson, normal distribution, or whatever. And for instance, an example of this is the height of people. Okay, how tall people are. And if I say that people are in average 1 meter and 60 centimeter tall, which is, let's say, here, then most people have a value which is very close to it. So maybe here you have 2 meters, here you have 1 meter and 40 centimeters, and nearly everyone is in the middle with a few exceptions here and there. Here people playing basket in the US, and other exceptions. While if you look at a power law distribution, you have something completely different. You have many observations here, which correspond to high value, to very small values, but a large number of observations. And you have a few observations, very rare, but with a very large value. So in our case, since we study the distribution of degrees, it means that here we have some connections, very few nodes, but with very large connections. And so one main difference is that if you look at the average of this distribution, it is probably somewhere around here. So you see that it's not at all representative of the whole distribution. Your average is far off the majority of the population. And the other important things is that you have here some values which are much bigger than here. So if I were plotting this on this chart, I will have something like this, and I will have some values here. So a typical example of this distribution is the wealth of individuals, how rich people are, where you have some people, you have many people in the world which are relatively poor compared to the average. And you have some people who are extremely rich, and the average is somewhere around here. So if you look at the average population, you take average wealth of individuals, and you design the price of a product based on this average. It's probably not a good idea, because you're designing you're fixing some price for people who do not exist, or who are rare, actually, not correspond to something common in the population. So it's very important to make the difference and to know if your network is rather like this or like that. And here you have an interpretation, an example in terms of networks. So for instance, in the US, if you have some transportation by train, you will usually have something, maybe roads or whatever, you have something like this. And if you look at airports, you can have something like that, because you can have some hubs with many connections, because there are no physical constraints, or not as much physical constraint, for instance, as. But there are many other explanations for this power law or bell-shaped distribution. Okay. So why is it called scale-free? Now, why we call it scale-free network? So one interpretation. Is just using this information. It means that your network does not have a typical scale. So you cannot look at some range of degrees, for instance, from degree, I don't know, 20 to 30, and say that this is the importance, this is the typical scale of my network. All the nodes which are more or less, a degree which is more or less, I can remove them and say that they are exception, they are just noise in my data or outliers, and my typical scales is from 20 to 30, from 20 to 30 or something like that. Here we are scale free, so it means that at every scale, everything is important. If the node with the highest degree, which is really extremely large, the Trump or Barack Obama of Twitter, they are important. Even though they are extremely rare, they are not outliers. They exist and they are important in your network. And all these people with very few connections, they are also important. You cannot just remove them and say that they are outliers. Another idea of scale free, which is a little harder maybe to defend scientifically, is that if you look at your network from far away, it will look like this. And if you zoom somewhere on some part, so this represents is a zoom on this part, then you get a network that relatively look like the same as the original one. So you cannot really see well on this. And then if I zoom in, I get this plot, and you see that it still looks a little bit like the same network. And if I zoom in, still look a little bit like the same network, and so on and so forth. So this idea of having a kind of a fractal structure, so a self-similar structure in your network, where, yes, at different levels, your network still have similar structure, similar organization. So this is the idea of scale-free network. Okay. Now let's do a proper definition to make some interesting observation about the properties of the degree distribution. So the problem is that with my initial distribution, with my initial definition here, I'm not respecting the proper definition of a degree distribution, which is that all the probabilities of observing my values should sum to 1. Right here, if I have this rule means if it were exact that the degree 1 will have a probability of 1, which is obviously not possible. So we add this constraint, and we also add the existence of a minimal degree. So as I explained before, usually we know that this power law distribution exists for some range of degrees. So maybe it doesn't work for degree 1, 2, 3, but it starts from degree 10. And so we add this minimal degree constraint. And from this, we can define the normalization constant, C, in order to have something which is properly defined. And from that, I'm not doing the details, but you get this proper definition of your degree distribution, your power law distribution. So let's look at in practice how does it look if you plot it. So here I plotted in linear scale, and in a linear scale I stopped at 10. So we have 100,000 samples, so I just generate sample with the distribution, and I get this shape with varying the exponent. Okay, so here the exponent is going from 2 to 3, which are typical values, and you see that it looks like this. So if you have the degree 2 represent 20% of the nodes, for instance. But what is interesting is that if I try to plot the whole distribution until the max value, which is here, on a linear scale, this is what I get. And obviously you see nothing because it's completely crushed toward the axis here, because everything interesting is happening there in a very small range of degrees. right? Here you have degree 0, degree 10,000, degree 20,000, but everything interesting is happening here. So that's why we plot these distributions on a log-log scale. And so the same plot as before. Now, if I have here 10, 100, 1,000, 10,000, I see that I have a line on my log-log plot. Okay, and you see that the exponent here, varying from 2 to 3, is actually defining the slope of the line. Okay, I have a line like this with exponent 2, and I have a slope like this with exponent 3. So your exponent is defining the slope of your line on a log-log plot. And actually, the slope of the line is the exponent. If you forget that this is a log-log plot and you take the slope, you get the exponent. So let's compare it. Yes. Yeah, so it's the same as it's related to the question before. The thing is that here this is very rare. These observations are very rare. So this means that you have one observation. This means that you have two observations. This means that you have three observations. And so because it's very rare, it becomes noisy. Maybe for exactly this degree, you get 0 observation, but then you got 1, then 0, 0, 1, 0, 0, 2, and so on and so forth. So it's completely normal that here it is very noisy. Because, well, one of the answers is because we are dealing with discrete observation. The degrees are discrete. So necessarily, when you get to something rare, you get something which is noisy. Okay, so nice. My power law looks like line on a log-log plot, but what about other distribution? So if I compare with the Poisson distribution that we already defined, here I take power law in blue. Okay, this line corresponds to a power law. Here I'm on a linear scale. In blue, I have my power law, and I tried to fit some Poisson distribution to look like my power law. So in this linear scale, maybe we see that they are not exactly the same, but maybe this red one does not look that different. But now, if I plot it on a log-log scale, you immediately see the difference between my nice line and the other ones, which decrease much faster. And in particular, you see here what we call the long tail, and which is very important when you have a scale-free network. It's the existence of these extremely large values, which are not very likely. It's noisy, right? But still, it's much more likely than in a Poisson distribution. So usually, if you don't have this long tail, you cannot really say that you have a scale-free network. You need to have some values which are very large in order to have really a scale-free network. We can compare also with something else, for instance, an exponential distribution. And again, if I plot on a log-log scale, I see the difference. Only the power law looks like a line. Okay, so this famous simple distribution, we see that they have very different properties. Okay, let's now define the moments of the scale-free distribution to observe something interesting. So the moments are defined like this. So the first moment is actually average. The second moment is the variance, that is skewness, and so on and so forth. And we know that the moments are defined by this equation. And now so I know that these are the moments, and if I replace here my this P probability of K by my distribution that I defined earlier, I get this, right? So this is going there, and then my alpha here comes there. So I have this definition. And if I do this, what I observed is that the moments are defined only if alpha is above m plus 1, where m is the moment. Okay, so first moment m equals 1, second moment m equals 2, and so on and so forth. And what this means, if we do the computation, is that the mean, so it is defined by it simplifies to this value, but it diverges for alpha below 2. So what it means that it diverges, it means that it's growing towards infinity. We will see in practice what it means just after. And for the variance, also we have this value. So the variance of a power law distribution is like that, but it diverges if your exponent is inferior to 3. Okay? And so the question you might ask is, what does it mean in practice that the moments are diverging? Because it means the diverging means that they are not properly defined. You should not, in theory, you cannot compute them, or they even do not exist. But in practice, if I give you, of course, a network, you can always compute the mean and the variance. So you can always compute them. So what does it mean that they diverge? Actually, it means that if you increase, so if you have a theoretical distribution, and you can get as many samples as you want. So the full population is, let's say, infinite. And what I give you is a finite sample of this infinite population. So I have, so let's take an example where the population will be 1 million elements, 1 million values. And I give you only 10 of them. So you compute the average, you compute the variance, and we compare this with the real value on the 1 million sample. If I give you only 10, you see easily that it's very sensible to noise, so it will be very different from the real value on the whole population, because maybe, I don't know, I had a good chance and I gave you one of the largest degree node immediately, so out of 10, this will make a value which is completely different from the value on the whole population. So if I give you a larger sample with 100 elements, you should get closer to the real value. If I give you 1,000 elements, you should get even closer, and so on and so forth. And what a diverging mean and variance means is that actually, until I give you the whole population, you won't have a good approximation of the real value. Because the moments, they are dominated by the long tail. It means that I will observe some, if I continue to observe new elements, I will find nodes which have a value so large that it will shift my mean, it will shift my variance towards a greater average value, a larger average value, or a larger variance. In practice, we can see it on some experiments. So here I'm using some degree distribution, not of degrees, but a degree distribution following a power law, and a distribution following a power law. And I'm increasing the size of the sample. So I start with only 10 nodes, 100 nodes, and so on and so forth. And I measure what is the mean of this sample and what is the variance of this sample. And I see that if my exponent is below 2, the larger the sample, the larger is the mean. And same thing for the variance. So actually what this means is that the mean depends completely on the size of your sample. So you should not rely on it, because it's just an artifact of the finite size of the sample. What I see is that if my exponent is between 2 and 3, then my mean is actually definite. So it will converge slowly, very slowly, towards the expected value. but my variance still increases towards infinity. And finally, if my exponent is is above 3, then I will have something that converges, but very slowly towards the expected value. So what this means in practice is that you should not rely on the average value if the exponent of the distribution is below 2, and you should not rely on the variance if it's below 3. So so an infinite variance is really, it tells you also that you should not, it's really this question of, even if you have an average, it doesn't tell you anything about the distribution because about the values of other nodes, because you have an infinite variance. So an infinite variance means that you really cannot say much about the values of other nodes based on the mean. Okay, so finally, I want to find, I already introduced the problem of finding the slope of the line of the log-log plot. So because if you find this slope, you can find the exponent. So your goal is to find the exponents to know if it's below 2, if it's between 2 and 3, or if it's above 3, to know what you can say about your distribution. One of the problems is that, so it's not really clear, but the green dots here correspond to, for instance, empirical observation. And as we already discussed, it's maybe clear in the beginning, but then it becomes very noisy around there. So it's not easy to find the proper slope. Where should I put my slope? On the red, the red one, the blue one? So I can do it manually, maybe just draw it with a rule and check what is the slope. The problem arises when you try to do it, for instance, using a regression approach by saying on the log transformed value. So you take this value, you take the log of the of the degree, you take the log of the frequency. So you get new values for x and y, and then you try to fit a regression with mean squared error fitting, for instance, and if you do that, you will obtain something that looks like the red line, because it will try to fit the noise, because it's not aware that this is actually very noisy, because it's due to a small number of observations. So if you want to do it with this approach, you should actually only fit maybe some part of the distribution which is well defined because you have many observations. But if you want to do it properly, you need to do it with maximum likelihood estimation. I won't go into details, but for instance, you have this paper which describes how to do it properly, and then you will correctly fit your exponents so that it matches the real data. Okay, so let's do that on some real network. So I take all this network as usual, and I compute the exponent. And what I observed is that in many cases, the values are between 2 and 3. Right? So you have some exception where it's 1, but many of them, a few above 3, but many of them are between 2 and 3. Yeah, so this means that actually the average value are not really, so usually we compute also the average degree, but this average degree is not very reliable since the convergence is very slow, as we have seen, and we have this infinite variance. So this average degree is not very reliable. So why is it between 2 and 3? Actually, there is a good reason for that. It's not magic. It's that if the exponent is smaller than 2, then the distribution is extremely skewed. So it means that you can have quite high probability to observe very large node. And if it's smaller than 2, then you have on a finite network a probability of observing nodes that has a degree which is larger than the graph, than the number of nodes. So obviously, it's impossible to have degrees to have in a network a node with a degree which is larger than the number of nodes in the network. So this should not happen unless it happens only on a small range of degrees. And why is it? It's not above 3? So if it's above 3, it means that the distribution is actually not that skewed. So you will so it will be closer to some Poisson distribution, for instance. All the nodes will tend to have relatively similar values, and it means that, for instance, if we take an exponent of 5, we can compute that to have a good probability to observe a single node of with a degree of 1,000 that we can consider large, we will have to observe 10 to the power 12 nodes. So obviously, this means that it's impossible if you have this kind of distribution and you have a social network on Earth. Since there are only 8 billion humans, it's very far from this value. So it will not be likely to observe nodes with a degree of 1,000. So it means that to observe properly a degree distribution which is power law and with an exponent of 5, you will need to have even more observation that there are humans on Earth. So not likely, not likely. Finally, the scale-free. So maybe I have to move to the last part, but we can show. It can be shown that the average distance in random networks depend on the exponent. So if your exponent is 2, the average distance is nearly a constant, because this means that basically you have a node which is connected to everyone. So if you have a node connected to everyone, the average distance between everyone is 2. Because you just have to go to this giant hub and to come back to any node. When you increase, so we have seen before that in a random network, in a normal Erdős-Rényi random network, you have a short distance which is in the logarithm of the number of nodes. And you see that if you have power law, you can define define that the average distance is even smaller than the logarithm of n. So it's because of this existence of giant node with large hubs, it will decrease the average distance between all nodes. Okay, so we can define a scale-free regime, which is between exponents 2 and 3, and where you expect to find most real-world networks. Okay, so this is the theory. In practice, what is really interesting is that there is a controversy going on in network science about do scale-free networks really exist or not? So Barabasi, I already introduced his name. It was one of the first to observe this scale-free property, and he proposed a model that I will introduce just after. Very simple, but which is a model explaining why you have this, why maybe you have this degree distribution. So he wrote a famous paper called The Emergence of Scaling in Random Networks, in which he introduced this model, and basically he's defending the idea that most real networks, nearly all of them, they are scale-free. So they have this power law degree distribution. On the contrary, you have, for instance, a famous researcher, a statistician, that wrote a paper in 2018 called Scale-Free Networks Are Rare. So obviously, he's defending the opposite opinion. And then you have another researcher, also quite famous, who wrote an article called Rare and Everywhere, Perspective on Scale-Free Networks, so trying to reconcile the two opinions. Actually, what was the clash happened actually on Twitter. So if you're following Barbasi and Closet on Twitter, you could see this fight going on in 2018. So you see, if you know Twitter, you can see on what side I was at that time. But so they were really discussing about this when the paper of Closet was released. And the argument actually of Closet is that if you look at actually there are some distributions which can really look like a line on a log-log plot, and in particular is defending the log normal distribution, okay, which the probability distribution of a random variable whose logarithm is normally distributed. And if you put a power law here, which is in blue. Yeah, it's the pale blue, I think. And you're trying some exponents of some parameters for your varying parameter of the log normal. Well, now you cannot really see which one is the power law and which one is the log normal. So if you take a proper statistical approach, you're not. It becomes much harder to say if a network is indeed a scale-free network or some other distribution. To sum up the discussion, so actually there was even a paper written this year on the topic. So it's a World Scientific paper dedicated to this controversy, and they are studying it as an epistemic clash. So it's really trying to understand why, and one of the reasons Jacobi is proposing in this paper is that it's because network science is a field which is interdisciplinary. So you have people coming from physics, you have people coming from statistics, computer science, and other fields, and they have a different vision of the world of science. And so it's normal that you encounter this kind of clash between interpretation because they have not been trained and they don't see the world maybe in the same way. So they try to define this properly in this paper, which is quite interesting to read. To sum up the arguments, the argument of Closet is that you have to make statistical tests, rigorous statistical tests, to say if it's scale-free or not. So I give you a network, I give you a degree distribution. If you want to prove, if you want to say it is scale-free, it is a power law, what you need to do is to compare it empirically with other proposed distribution and to check to which distribution is it the most similar. So you compute p-values, you check if it's the most similar, and you can say yes, it's a scale-free, or no, maybe it's not exactly a scale-free. The vision of Barbasi is different. This vision is that to have something, what is interesting to have is a good model. You need to have a model which is simple and which explains reality. So networks are real objects. So the argument against the argument of Closet is that networks are real objects. They are not mathematical abstractions. So your degree distribution is noisy, and this is normal because it's a real world. So for instance, I don't know, if I look at a friendship in a social network, well, this social network has a history, it has limitations, maybe he limits the number of friends, maybe it makes harder for people with a certain degree to get some connection and easier, or incites people with low number of friends to get connection, or it removes them, or whatever. So it's not a mathematical abstraction, it's reality. So it's normal that you cannot fit it perfectly with a mathematical function. What he observed is that power law is a good and simple model of degree distribution. So it's very simple. It has a single parameter, and yet it seems to look a lot like reality. And there are many years of research which is based on the observation of this scale-free networks on the topic of the scale-free networks. So it means that it is meaningful because there is all this obvious research. So actually, I think the two are interesting, and there is not a right answer, certainly, but it gives you an idea of this controversy. And so I think I did not put it here, but on the cheat sheet, I added a kind of a way how you should behave relatively to this controversy when you have a network. So maybe you don't care. Actually, in many cases, you don't really care to know if it's really scale-free or not. What you need to know is that it's not a bell-shaped and you have some very large degrees, and maybe that's enough for you. Only if you want to really say that it's scale-free because it's important for you to explain maybe how this network was created or that it has some properties, then you need to really think if it's really scale-free or if it's explained by something else like a log normal. So finally, the model of Barabasi and Albert. It's actually a very simple model. It says that maybe what we overlooked is that networks are evolving. They are not created from nowhere. They do not appear from nowhere. They start small and they grow. And so what he proposed is that there is a simple mechanism called preferential attachment that can explain the emergence of this power law degree distribution. It's very simple. It says that you start with some random network, a small random network, and then you add nodes one by one. And for each node you also add a few edges connecting this node that you just added to some random nodes in the network, which is already here, right? So you add, I don't know if I have yes, I have the algorithm here. So we add, at each step, we add m links. And the probability of these new links to connect is not uniformly random. So you don't connect to everyone at random. You connect to nodes according to, with a probability which depends on their degree. Okay? So if you have a node with degree 100 and a node with degree 50, you have twice the probability to connect to the node of degree 100 to the node of degree 50. And obviously what will happen is that the nodes which are there in the beginning, by chance, because they were there in the beginning, they have a higher degree after a few additions. And then since they have a higher degree, they will attract more edges because they are more likely to be connected by the new ones. And their degree is growing, so they attract more nodes, and so on and so forth. So this is this can be understood as something I already described. I think it's a rich get richer phenomenon. So if you already rich, it's easier to become rich. And this also is something that we can understand in many networks. For instance, on Twitter, if you're very popular, if you have all these people who are very already popular, so they have a very large incoming degree, they have many followers. So when a new person joins Twitter, he is quite likely to look at who, for instance, his friends or her friends are following, and to follow the same people. So since Barack Obama was followed by many people, then you have a good chance to see that he is someone interesting to follow and to follow this person. So for Barack Obama, there are other reasons, obviously, but for some celebrities which are famous mainly because they are famous on Twitter, then this will be the only reason why you can follow them. And if you apply this simple mechanism, then you will end up with a degree distribution that has an exponent of exactly 3. And this does not depend neither on the number of nodes you have in the beginning, nor on the number of edges you add at every time. It's always this value as long as you use this mechanism to add edges. So the path length is actually defined by this value because the exponent is 3. That's what I already introduced before. The clustering coefficient, on the contrary, can be shown to be small, exactly like in normal random network, Ardor-Srény or configuration model. You have the same problem. You don't have a high clustering coefficient. So you explain, you are explaining the degree distribution with a simple mechanism, preferential attachment. You still have your short average path, but now you don't have a high clustering coefficient. So just to finish, there are of course a lot of other random networks that have been proposed. I won't present them in detail here, but just so that you know them, they are much less famous, obviously. And one of them, for instance, is the vertex copying model. So the idea is very simple. It's like in the Barabasi model, you add nodes one after the other. But this time, to try to impose some local structure, which is lacking in the Barabasi model, when you add a new node, you choose a target node, and you check what are the connection of this target node, and then you will have a higher probability to connect with the neighbors of this node. It's like if you were introduced in the network by someone, and so you have a higher probability to connect to the friends of that person. So this will add some local structure to your network. There is also the Holmkin model, which has introduced to have a more realistic clustering coefficient. And yeah, that's all. So what you see is that you can have other models that have all three properties, but the question is, what is the point? Because now you have defined some random model, which is quite complicated. You need to take other neighbors. You need to have some parameters. So in the end, okay, you can get the degree distribution, the pattern, and the clustering coefficients. But well, what can you say with that? So the idea is that a model is useful. All models are wrong, but some models are useful. So the model of the small world model has an argument to show that a simple mechanism was able to make emerge the high clustering coefficient. The Barabasi model has made a simple argument that you could explain a scale-free network. These models really, the goal is really to make a point. Simple mechanism can explain something we observe, and which is not observed in random network. On the contrary, the first model we have seen last week, Ardor-Srény and configuration model, they are used in practice for many things in network science because they allow to compare what is happening in a real network with a real-world version of it. While you cannot really create a random network which looks like your real network using the Barabasi or the Watts-Strogatz model. They are just here to make a point, generate a network, run and observe some property in it. And finally, so as I said, you can propose new complex model that will make some properties emerge. But the problem is that the fact that you have a correlation, that you have the same property, is not really a good explanation. It's just, okay, this mechanism makes this emerge, but this is not necessarily what's happening in real life. So we have seen maybe that sometimes the shortcuts could have an explanation in social network. Maybe the Barabasi Albert could have also an intuitive interpretation. But it's only partly true. So this model can be interesting to model some particular phenomenon if you want to study something precise. And I'm finished with my slides. So as usual, you have some experiments about scale-free network here, and we can make a short break first.